Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, this is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. In this video, we continue on into transformations of functions. We've already done vertical and horizontal shifts. We have dealt with reflections about both the x and the y axis. We spent a moment talking about even and odd functions because that's going to come into play a little bit later, maybe even in this section. And then finally, now we're going into graphing functions using stretches and compressions. And this, honestly, of all of the topics, ends up being a little bit of a challenge for people. So let's go ahead and read off this theorem here. So vertical stretches and compressions. Given a function, you have a function named f, a new function g of x, which in this case we're going to call g of x a times f of x, is just a vertical stretch. I'm going to use yellow for the stretches. A vertical stretch or a vertical compression. It's a stretch if a is greater than 1. So you multiply your function by 5. It stretches all the y values away from the x-axis by a factor of 5. If, on the other hand, that coefficient a of f of x there is between 0 and 1, well, that is a compression. So again, maybe I'll highlight the word vertical compression here as well. If a, in this case, and I'll give an example here, suppose a was 1/3 of the function x squared, well, that means all the y values are 1/3 of what they normally would be. And so they're a lot closer to the x-axis than what they would be. A lot of students see this as a wider graph, but it's actually not true. It's closer to the x-axis. And then I didn't actually show a graph of a vertical stretch, but if I wanted to show a graph of y equals 3x, 3x squared, that just means all the y values are multiplied by 3, so it rises a lot faster. 3 times faster is one way to think about it. And again, a lot of students will say, oh, that's just narrower. So we have a narrow function and a wide function. And that's a misnomer. It's not true. But a lot of people see it that way at first. I'm going to give you an example, though, which will kind of obliterate that mindset. Finally, the last little line here, if a is negative, then there will be a combination of a vertical stretch or compression with a vertical reflection. We went through in the lecture prior to the last lecture and talked about if you were handed a function that had a negative lead coefficient, so a negative in front of a function, so negative sine of x, for example. That would look like the sine, but it would be reflected about the x-axis. Well, this last line just says, well, not only can you have a reflection, but if there's a 2 in front of that, then it's reflected and stretched by a factor of 2. All right, so that kind of starts combining a lot of our transformations. Let's go ahead and look at a couple examples here. This first example actually is kind of oddly worded. That's my fault. I was the one that created it. But let's create a table for a fictitious function f. So I'm just make something up. X versus f of x. Doesn't really matter what it is. So I'm going to say, we'll go from, let's say, -2 to -1 to 0 to 1. You could use any, actually I'll go all the way to 2. Use any y values you want, as long as it's a function. So let's do y values like 9 and 3, 6 and 0, and I don't know, -12. So if you wanted to plot those points, I suppose they didn't ask us to, or I didn't ask you to, but let's go ahead and plot those points anyway. So here's -1, here's -2, and I'll go ahead and symmetrically write 1 and 2 here. The scale I just wrote down is ridiculous, right? So we're going to go ahead and say that this is 3, 6, 9, and 12. Again, 3, 6, 9, and 12. So negative 12's down there, positive 12's up there. All right, now let's plot some points. And I'll use black for this, for the points here. So negative 2, comma 9, way up here. I'm not going to label them. Negative 1, comma 3, 0, comma 6, 1, comma 0, and finally 2, comma negative 12. So that is a tabular function. Nothing really crazy. But now we're going to look at g of x. And in the instructions, I just say, well, now that you've created your table, let g of x, which I'll write in blue here, be 1/3 of f of x. That's why I chose numbers that were all divisible by 3, to be honest with you. So g of negative 2 will be 1/3 of 9, or in other words, 3. G of negative 1 will be 1/3 of 3, or 1. G of 0 will be 1/3 of 6, which is 2, and so on and so forth. 1/3 of 0 is 0. 1/3 of negative 12 is negative 4. And in blue, I will plot g. So here's negative 2, comma 3. Negative 1, comma 1 is probably right around here. 0, comma 2 is right about here, maybe. 1, comma 0, same spot. Y values are the same, so 1/3 of 0 is still 0. And finally, 2, comma negative 4, so that might be around here. And that's the idea with a compression. It just causes the y values to be closer to the x-axis. These are all 1/3 of the original distance to the x-axis. By the way, you could have done this in Desmos as well, but it's probably just better to do it by hand. Now, generally speaking, people are pretty okay with vertical stretches and vertical compressions. However, horizontal stretches and compressions are a completely different beast. People generally, that's where people fall apart a little bit, so we're going to spend some extra time on this. Given a function f, we can create a brand new function, g, and g would be defined to be f of b of x. Now notice b is multiplying x there, right? Just like in the previous theorem, our coefficient a was multiplying f of x. Here, b is multiplying x, so f of b of x. Let's see, it's a horizontal stretch or a horizontal compression. So let's go ahead and use the highlighter again for the stretch part and the other highlighter for the compression part. And when I say horizontal, I mean compressed toward the y-axis, like an accordion. Compressed towards the y-axis or pulled away from the y-axis. Again, like an accordion. Well, remember, actually, in fact, I'll hop back a couple. If you were dealing with vertical stretches or compressions, if the coefficient a there was greater than 1, then it was stretched, right? Vertically stretched away from the x-axis, because you're multiplying all the y values by a number greater than 1. That is not the case with horizontal stretches and compressions. With horizontal stretches and compressions, if b, that number that's multiplying x, if that's greater than 1, then the graph is compressed by a factor of 1 over b. So if b was, let's say, 3, then the graph would be compressed by 1/3 toward the y-axis. And we'll discuss why in a moment. On the other hand, strangely enough, if b was between 0 and 1, like let's pretend you had, I don't know, f of 1/2 x, that will actually stretch by a factor of 1 over 1/2, or in other words, 2. It stretches basically by a factor of the reciprocal of that coefficient. So everything would be stretched by a factor of 2 away from the y-axis. And the same notes that I said before, if b is negative, it'll flip about the y-axis. This is honestly one of the harder concepts for people to get. So I think rather than going into my next example, I think what I'm going to do is just showcase this in Desmos. I think it's much easier to see than to talk about. Now you can see, if you've been watching these lectures all in a single day for transformations of functions, you can see that I'm still filming on the same day, because this was all about the vertical shifts and the horizontal shifts. So let's go ahead and just get rid of that stuff. And I'm going to put a coefficient of A on this and a coefficient of B on that. Remember, A is on the outside, B is on the inside, which means that A will do vertical and horizontal, or vertical stretches or compressions, and B will do horizontal stretches or compressions. And this is going to pretty much ruin your idea of what a vertical stretch or compression looks like. Let me change this to x squared for the time being, because I drew that as an example and I said, oh, if you increase, it gets narrower. That's what a lot of students say. If I increase that coefficient there, right? So it's greater than 1, so it looks like it gets narrower. Or if you decrease it to less than 1, it looks like it gets wider. And that is an optical illusion. It really just compresses. When A is less than 1, it compresses toward the x-axis, and when A is greater than 1, it stretches away from the x-axis. So let's actually see that optical illusion in action using the sine curve. Here I go. I'm going to change A to be larger than 1. And you can see it's not that it gets narrower, it just gets taller. And if you know anything about signal processing, like sound waves, this means you're increasing the amplitude of the sound. It gets louder. If you decrease this, we can go all the way to 1. Once you get below 1, it starts to compress that toward the x-axis. So there's a good visual of that. Now, on the other hand, remember, if I increased A, it would stretch vertically, right? But if you increase B, it does not stretch horizontally. It actually compresses. It gets closer to the y-axis. And the reason why that's true is one simple thing, and let me see if I can quickly just relabel these x-axis values a little bit better. Well, there we go. I have them labeled in terms of pi. Now notice, you should know that the sine curve goes through one full cycle every 2 pi. One full cycle every 2 pi. If I increase this to, let's say, 2, it now goes through 2 full cycles every 2 pi. If I went to 3, well, you probably would guess it. It goes through 1, 2, and 3 full cycles in that same amount of time of 2 pi. And so as you increase B, you're actually making the function occur faster. You're compressing the function horizontally so it goes through more movement in a shorter amount of time. That's the basic idea. If you were to start at 1 and decrease pi, you stretch out, or sorry, not decrease pi, but decrease B, you stretch out the curve like a really loose slinky. It's kind of a good way to think about it. There you go. I've stretched it out, and now if I increase it, it'll compress it. So there's a good visual of the effect of B. So now we're back onto the lecture page. Let's go ahead and see what our first example is. Graph the function 1 over 3t squared. This is actually a stretch or a compression. You just have to be willing to spend a little bit of time rewriting it. This is h of t is equal to 1/3 times 1 over t squared. And you know what 1 over t squared looks like. 1 over t squared normally looks like this. And by the way, it does have a vertical asymptote on the y-axis. And it has a horizontal asymptote on the x-axis, which for some reason I couldn't draw. So let me draw it again. Okay. So there's my horizontal asymptote on the x-axis. or t-axis, I guess, since that's really the letter I'm dealing with. And what we're going to do is compress this. In fact, I'll point an arrow at that. And there I've written down, we're going to compress this vertically by a factor of 1/3. Now remember, this is one of our base graphs. It goes through 1, 1 and -1, 1. Now to be very, very honest with you, there are several graphs that are very hard to see compressions or stretches with, and this is one of them. This is very difficult to showcase a compression with, and I'll show you why. I'm going to go ahead and copy that graph as much as I can. The vertical and horizontal asymptotes are not going to change. You're squeezing things toward the x-axis. Well, nothing like, for example, the horizontal asymptote here is not going to get any closer to 0. 1/3 of 0 is still 0. And the vertical asymptote's going to remain the same. And you're going to redraw your function, but all the y values are 1/3 of what they used to be. So essentially, and it's really challenging to really make it look correct and different. Let me see if I could zoom in here because my hand seems to want to really mess up this graph. All right, I got that side down. Try to make it as symmetric as possible. Notice when I graph, I use a lot of kind of slashes with my ink, and that's mainly because it's the best way for me to get a decent graph going on. Now, those 2 points were at 1 and -1 for the t values, and their y values were both 1. Well, in this case, instead of being at 1, 1, this point's at 1, 1/3 of its original y value. And on the other side, -1, again, 1/3 of its original y value. And if you look at those two graphs, they're essentially the same. It's really, really difficult to showcase a compression or a stretch of a reciprocal function like this. But there you have it. That's how you would do a compression of a reciprocal function. And I just decided to kind of show really quickly what these two graphs look like compared to each other. And you could easily see, yeah, they're the same graph. It's just the blue graph is 1/3. It's all the y values are just a little bit below. So for example, at -0.99, I have 1.02 as my output on the original function, but now it's 0.34 on the new function. So they're just 1/3 the values. Now the last example here is really just to make sure that you can work with graphs if you have to. So the functions f and g are related to each other. And it says relate the function g to f. In other words, f will be our anchor, and g, we're going to figure out how to write g in terms of f. Or maybe, yeah, g in terms of f. Let's just do it that way. And if you think about it, they both have the same heights, right? So the height right here for this point is the same as the height right there for that point. The height for that point is the same as the height for that point. So there is no vertical compression or stretch going on, but horizontal definitely, right? Everything's been kind of squished for that orange function g. Everything's been squished toward the y-axis. Now, by how much? By what factor? What did you multiply f by to get to g? Well, the x value here was 6. And now when we multiplied or did something to f there, that x value became a 2. So it looks like we went and took 1/3 of 6 to arrive at 2. And if you said that, you would not be wrong. But g is not, let me give you options actually. I'm going to give you some options to think about. I'll say, is g of x, is that 1/3 of f of x? If so, why? If not, why not? Is g of x equal to 3 f of x? If so, why? If not, why not? Put a little question mark there. Is g of x equal to f of 1/3 x? If so, why? If not, well, why not? And finally, is g of x equal to f of 3x? Again, if so, why? If not, why not? We definitely know it's something with a 3 though, because to get from 2 to 6, you multiply by 3. To get from 6 to 2, you multiply by 1/3. So it's something to do with that 3. Well, let's just throw out the ones that are kind of easy to see. If g of x was 1/3 f of x, it would look like this. All the y values would be 1/3 what they normally are. So it'd be something like this. What's that, 3? So it'd go down to 1. It'd be something like that. That is 1/3 of f of x. All the y values are 1/3 of what they were originally. And that's definitely not what g looks like. So we can kind of get rid of that. That's not what we're looking at. And by the same argument, it's definitely not that g of x is 3 times f of x, because if that was the case, this point at a height of 4 would be at a height of 12. It'd be off the screen. So it's definitely not the second case either. So this is gone and this is gone. So we're really down to the g of x equals f of some number times x. And remember, by our theorem, f of some number times x is either a horizontal stretch or horizontal compression of our original function. And this is definitely a horizontal compression toward the y-axis. The question is, which of these two? Well, if you refer back to the theorem, and maybe I'll hop over there really quickly. If b is greater than 1, then the graph will be compressed. And that's actually what we want. We want the graph to be compressed. So if b is greater than 1, the graph will be compressed by 1 over b. So that's our big clue. If you look at those two options, the one that has the b, the coefficient of x that's greater than 1, is this guy. That is a compression horizontally by a factor of the reciprocal of that, 1/3. And that is exactly what we want. We want our x values to be 1/3 of what they were originally. So this is the winner. This one is not. Let me go ahead and cross that out. This one's not, because that's actually a horizontal stretch by a factor of 3. And that would mean that you have something way out there. So this must be the winner. I'll just write it this way. G of x is definitely equal to f of 3x. Again, it's because everything that normally happens between 0 and 6 for the function f now happens 3 times faster. So it happens between 0 and 2. That's really how you can think about it. It's a really nice way to think about horizontal stretches and compressions. Now, that does it for this video. I like to kind of keep these topics kind of short. So the next video, we're going to combine all the transformations all at once and do some bigger problems for graphing. These are going to be kind of the end-all be-all types of problems.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.